Recording in progress.
Now, what will happen when I couple zinc electrode and the copper electrode? Look here. So we have calculated the standard electrode potential of copper. So this is copper 2 plus ion. This is copper metal dipped in copper 2 plus ion. And this is zinc metal dipped in zinc 2 plus ion. So many information you are getting from this: zinc in zinc 2 plus, copper in copper 2 plus, and they are coupled. And the solutions are connected through a salt bridge for electrical neutrality. Now, the reduction potential of copper electrode is a plus 0.34, and the reduction potential of zinc, actually this is a standard reduction potential. Standard reduction potential is minus 0.76 volt. You should understand one particular thing here. When you couple two different electrodes with two different electrode potentials, that electrode with more positive reduction potential will undergo reduction. Which will undergo reduction? That electrode with more positive reduction potential. Suppose you look here, hydrogen is at 0. There are so many elements below hydrogen with a negative. Suppose if this is -1, -2, -3, -4, something like that. And there are number of elements with the positive reduction potential, +1, +2, +3, something like that. If you couple the -1 and the -2 together to form a cell, the reduction potential with the -1 will undergo reduction, and the reduction potential with the -2 will undergo oxidation. So you should understand this particular point. Suppose if you couple +2 and +3 together to form a cell, the +3 will undergo reduction and the +2 will undergo oxidation. That is why in general we say any element in a particular level in the electrochemical series will displace that which is above that from its solution. See, zinc is here means zinc will become zinc 2 plus by redisplacing copper 2 plus into copper, because zinc is below and the copper is above. So if you take a hydrogen, zinc is below, so zinc will displace hydrogen from its solution. That is why when zinc reacts with hydrochloric acid, hydrogen is released by forming zinc chloride. But if you take a copper and dissolve it in hydrochloric acid, nothing will happen. Both are metals. But the copper is not displacing hydrogen from its solution. But zinc is displacing hydrogen from its solution because the electrode potential of zinc is below that of hydrogen. So number of questions are asked with this understanding. Which will displace which element? What is the position of that particular element in the electrochemical series? You should understand this. Now I am coupling these two. So between zinc electrode and the copper electrode, copper has more reduction potential, therefore that will undergo reduction. So copper 2 plus +2 electron giving copper solid. Zinc will undergo oxidation. Zinc will become zinc 2 plus +2 electron. So the overall cell reaction is zinc solid plus a copper 2 plus giving zinc 2 plus copper solid. So this is the overall cell reaction. So now you are going to calculate the cell EMF. EMF of the cell is equal to electrode potential of the right hand side electrode minus electrode potential of the left hand side electrode. If I say simply electrode potential, I am meaning the reduction potential. So on the right hand side it is plus 0.34, minus 0.76. Therefore, this becomes plus 0.34 plus 0.76. So the voltage is 1.1 volt. So this is how any cell is constructed. Any cell is constructed. Now, the hydrogen electrode, what we have used as the standard electrode to measure the electrode potential of any other electrodes, has a few drawbacks. Number one, maintaining the purity of the hydrogen is difficult. Number two, maintaining the 1 atmospheric pressure of the hydrogen gas bubble is another difficulty. So, in order to overcome these difficulties, another standard electrode is constructed, and that electrode is called calomel electrode. What is calomel electrode? Calomel means mercurous chloride. This is mercurous chloride, Hg2Cl2. You may ask, sir, we are writing sodium chloride, one sodium, one chlorine. We are not writing Na2Cl2. Why don't we write mercurous chloride and HgCl? See, mercury can exist in two different oxidation states. One is Hg plus, which is mercurous, and the other one is Hg2 plus, which is mercuric. The mercurous ion is always existing as dimer. So mercurous ion is always written as Hg2 2 plus. So Hg2 2 plus is with the two Cl minus ions. So mercurous chloride is Hg2Cl2. What is this, a calomel electrode? Calomel electrode is much more reproducible than standard hydrogen electrode. And the calomel electrode has a standard reduction potential of 0.2422 volt at a 25 degrees centigrade and with a saturated potassium chloride solution. See, the construction is very simple. Is having a glass tube with mercury in contact with mercurous chloride, and there is a platinum wire for contact, and above this mercurous chloride, saturated potassium chloride solution is kept, saturated solution, and there is a side tube for solution contact. This is the construction of calomel electrode. The electrode reaction is mercurous chloride plus 2 electron giving 2 mercury liquid plus 2 Cl minus ions. This is the electrode reaction of calomel electrode. So the calomel electrode is reversible with respect to Cl minus ion. So now you can couple calomel electrode with any other electrode, and you can find out the cell EMF. So this is calomel electrode. There is another famous electrode which is very often asked. I think, is it clear now? Yes, sir. Another important electrode you should understand is quinhydrone electrode. What is this, a quinhydrone electrode? This is called quinone. Quinone. Quinone coupled with hydroquinone. This is called the quinol or hydroquinone. The quinidrone electrode is reversible with respect to H plus ions. This is represented as Q. This is represented as QH2. Equimolar mixture of a quinone and hydroquinone is called quinidrone. It's called the quinidrone. Now, according to Nernst equation, that is Nernst equation, EMF is equal to E0 minus RT by NF ln reduced concentration divided by oxidized concentration. So E0 minus 2.303 RT divided by NF log of reduced concentration QH2 divided by Q. F is a Faraday. 1 Faraday is 96,500 coulomb. R is universal gas constant 8.314 joule per Kelvin per mole. T is a temperature. If it is taken at 25 degrees centigrade, then the whole value becomes E0 minus 0.0591 by N, where N is the number of electron transfer, log of QH2 by Q. This E0 is called the standard electrode potential. Standard electrode potential. This E is electrode potential at any other temperature or any other concentration can be calculated. So this is another important idea you should always remember. This quinidrone electrode is actually used to find out the pH of a solution. If you want to find out the pH of the solution, then this quinidrone electrode is used. Any doubt?
No, sir.
See the molar conductance of, watch the problem carefully. The molar conductance of sodium chloride, hydrogen chloride, and sodium acetate at infinite dilution. At infinite dilution means when the solvent is in large excess, which means that it is assumed that all the electrolytes are dissociated, found to be 126.45 Siemens centimeter square per mole, and for HCl it is found to be 426.16 Siemens centimeter square per mole, and that of sodium acetate is found to be 91.0 Siemens centimeter square per mole. Now, you are asked to calculate the conductance of acetic acid at infinite dilution. This is the problem.